This is Unit 4, Similarity. Preview video 4.3, Parallel Lines and Similar Triangles. Take a deep breath. Ready? Inhale. Hold. And exhale. Close your eyes for like 10 seconds. Take a deep breath. Alrighty, friends, you have here, don't forget date, time, location, and a parental sign-off. What are we doing today? We are doing these three things. We're going to explain the difference between congruency and similarity. And we're going to highlight shortcuts to both. What's the difference between congruency and similarity? And highlight the shortcuts to both. We're going to explore the relationship of dimensions and similar ratios. And we're going to demonstrate how parallel lines create similar triangles and proportional segments. These are the three things we're doing. Okay, congruency. We're going to explain the difference between congruency and similarity and highlight shortcuts to both. Congruent triangles have the same shape and the same size. Congruent triangles are same shape and same size. That's congruency. Similar, they have the same shape, but they're just different sizes. Like clothing, small, medium, large. Same shape of the clothing, but different sizes. Same shape, different size. Both of them have shortcuts to that. So for congruency, we asked ourselves if sides or angles, side congruency and angle congruency are minimally true, then the triangles are congruent, and that would be same shape, same size. So congruent sides and congruent angles. And of course, you're familiar with these. Side, side, side congruency, side, angle, side congruency, angle, side, angle congruency, and angle, angle, side congruency. This is shortcuts to same shape, same size. Now for similarity is if you have a combination of not side congruency, but side ratio equality and angle congruency. If a certain combo of side ratio equality and angle congruency is minimally true, then the triangles are, whoops, this should be changed, similar, which is the same shape, different size. Cut and paste that wrong. Similar, same shape, different size. And there's 3 of them. First one is angle, angle, and you have to use the similarity sign. If you don't use the similarity sign, you will be marked down. So it's angle, angle, similarity. And what angle, angle, similarity says, if you have a minimal of 2 sets of congruent angles, angle, angle, then the triangles are similar, not congruent, similar, same shape, different size. A very common example of this would be a larger triangle. Let's say there's a right angle here and then a smaller overlapping triangle, right angle there. And so the larger triangle, trace it, smaller triangle, trace it. In this scenario, you have a pair of right angles which are congruent. They're also corresponding. And then they share this toe angle, which is reflexive. And so this would be an example of angle, angle, similarity. This by far is the most common. Put a little star by that. Angle, angle is the most common. Angle, angle, similarity. Then you have side, side, side. Similarity. Notice that little similarity sign. It says this. Let's say you have a triangle whose side length is 3, 4, 5. And another triangle whose side length is 6, 8, 10. Watch carefully. If I reduce 6 to 3, and I get a 2-to-1 ratio, keep working it around, 8 to 4, that also reduces a 2-to-1 ratio. The last one, 10 to 5, 2-to-1 ratio. Notice, it's not that the side lengths are congruent, but it's the ratios that are equal, 2-to-1, 2-to-1, 2-to-1. So if you have all 3 side ratios, and we use equal, not congruent, because ratios is a number, then the triangles are similar. Side, 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 similarity. You use the same numbers, 3, 6, 4, 8. So this one is side angle, side similarity. It says this, congruent angle, that if you have a set of sides, if I reduce that, it's a 2-to-1, and another set of side ratios, if I reduce that, it's also 2-to-1. So if I have a set of side ratios, another set of side ratios, and a congruent angle in between, then the triangles are similar. This is called side angle side similarity. So equal side ratio, congruent angle, and another equal side ratio. Then the triangles are similar, same shape, different size. Why is it important to establish similarity? Because the minute something is similar, you know that all your angles are congruent and all the side ratios are equal, which means you can start working the triangles like this with a proportion. We're going to name the similarity that's being demonstrated here. So right here, let's trace the overlapping triangles, and it's kind of good to just quickly pull them apart. If you have 2 different colors, that is kind of helpful here. Same shape, different size. Let's take a look at what we have here. We have a pair of congruent angles. And then both of them overlap and share this angle. So this demonstrates angle, angle, similarity. Same shape, different size. Let's try this one. Ready? Let's pull these triangles apart. Pull the numbers over. This is 10. This, careful, is not 24. It's 24 minus 9, which is going to be 15. And then here's our larger, change colors, larger triangle. Pull those numbers over. This whole side is 16. This is 24. And then they share, of course, this reflexive angle right here, right there. They share this angle. So they have a shared angle, so we're going to put an A here. Let's check our ratios. Okay, check our ratios. 10 to 16. We know 2 goes into both of these. 2 goes in here 5 times. 2 goes in here 8 times. Let's check this one. This is 15 and 24. 3 goes in here 5 times. 3 goes in here 8 times. Notice the ratios are the same. So we have side angle side ratio, similarity. This is your page. Hit pause. All right, welcome back. Hopefully you actually did your own work, folks. You get your red pen out. I want to see the corrections. So very quickly, let's check here. Because of the parallel lines, you do get armpits of the Z here. Armpits of the Z, what gets you a pair of angles, actually going both ways. You also have a pair of vertical angles. So these would be similar, not congruent, by angle similarity. Down here, let's check our ratios. We're going to go short to short and reduce. That's 12. 6 to 18. 6 goes in here twice. 6 goes in here 3 times. Let's go medium to medium. So that's going to be 26 to 39. 13 goes in here twice. 13 goes in here 3 times. And then 28 and 42. 14 goes in here twice. 14 goes in here 3 times. Ratio's the same all the way around. This is side, side, side similarity. Now, before we move on, we need to talk really carefully about something that interesting that happens. Is that you need to explore the relationship of dimensions and similar ratios. The first dimension is 1D. First dimension is only length. So perimeter is a length concept. Perimeter is a one-dimensional concept. So if I have a ratio of similar shapes, a small and a larger rectangle, the ratio of the sides, let's just call it X and Y, and dimensions, it's going to be to the first power. The same set of similar rectangles, if we were to deal with area, area is a two-dimensional concept. So that ratio is going to change to X squared, Y squared. And if you go into volume, volume is 3 dimensions. Therefore, it's X cubed, Y cubed. Therefore, the exponent of the ratio changes with the dimensions. Let me give you a practical example. Very practical, very simplistic. We've done this in class before. Okay, you learned probably in 3rd or 4th grade, this really simple concept that 1 yard is 3 feet. So you learned this ratio, that yards, 1 yard equals 3 feet. Problem with that is it's only true in the first dimension. Come down here. Let's make ourselves a square yard, which is 3 feet one way and 3 feet the other. So when you change the dimensions, you change the ratio. Now, 1 yard squared equals 9 feet squared. You see we squared those? And it gets even trickier if you had a cube made up of a yard. It's going to be 3 feet this way, 3 feet this way, and then 3 feet going in depth, which if this was made of a bunch of cubes, it would be 1 yard cubed, and there'd be 27 feet cubed, or sugar cubes, if you will. Think of it as sugar cubes. So the dimensions change, the ratios change with the dimensions that you're working in. Keep that in mind. Things, the exponent of the ratio changes with the dimensions. Things that have the same dimension have the same ratio. So when you're dealing with similar triangles, the ratio of the sides, a side length over a side length, side lengths are 1 dimension, is going to be the same ratio, walk it around like this, as the perimeters. Perimeter over perimeter. And the reason why is because perimeter is also 1 dimension. So the ratio of the perimeters will be the same as the ratio of the sides, because things that have the same dimension have the same ratio. We'll do an example together, just one. So it says right here that EFG is similar to PQR, similar. So we're going to write EFG, PQR. EFG is larger than PQR. Side E to F is 12 centimeters. P to Q is 8 centimeters. The perimeter of the triangle EFG is 36 centimeters. And we want to find the perimeter of PQR. So because side lengths are 1 dimension and perimeter is 1 dimension, they share the same ratio. So we can, our scale factor 12 to 8, we're going to reduce that. 4 goes into both. 4 goes in there 3 times. 4 goes in there twice. So I have a 3 to 2 side ratio and a 36 to unknown perimeter ratio. Cross multiply. So we have 2 and 36, 3 and x. The key to multiplying is not multiplying. So I'm not multiplying the 2 and the 36. I'm just going to factor it out. Bring the 3 over. I know 3 goes into 36 12 times. Therefore, our unknown perimeter is going to be 24 cm. The exponent of the ratio changes with the dimensions. Watch this carefully. Mr. Thomas and Mr. Liu have rectangular yards which are similar. Same shape, different size. The width of Mr. Thomas's yard is 15 feet and 30 feet in length. The scale factor of Mr. Thomas's yard, so the left is Thomas and the right is Liu. The scale factor is a 3:4 ratio. We want to find the area of Mr. Liu's yard. So watch what happens here, because there's a very subtle difference. Scale factor is a side-to-side ratio length. Scale factor by definition is only one dimension. So our one-dimensional ratio is 3:4. Our two-dimensional ratio, which is what we need because area is 2 dimensions, is going to be 3 squared, 9, 4 squared, 16. So we find the area of Mr. Thomas's yard, which is 30 times 15, which is basically 15 times 3, and you add a 0. So the area here is going to be 450, and it's going to be feet squared. So we're going to make a ratio of area to area. So Mr. Thomas' area is 450 feet squared. Mr. Liu's area is the unknown feet squared. The ratio, however, that we are using is not 3:4, because 3:4 is only in the first dimension. We need the second dimension ratio. So this is 9:16. Cross multiply. We're doing 450 times 16 equals 9x. Some of you are about to have a heart attack because I'm not even using a calculator, because the key to multiplying is not multiplying. It's factoring. So I'm going to go divide by 9. 9 goes into 45. 5 times, add a 0. So it's 16, basically, times 5. And then I'm going to add back that 0. So the area of Mr. Liu's yard is 800 feet squared. When you change dimensions, you change ratios. Make sure you set this up correctly. Watch what's changing here. The area of PQR is 20 cm squared. What is the area of EFG? Pause. Solve. Welcome back. You should have a red pen. You're like, Miss Way, I don't know how to find the area of a triangle. You don't even need to. Watch. First, you find your scale factor, and this is a 3:2 ratio. So your first dimensional ratio is 3:2. Your second dimensional ratio, 3 squared, 9, 2 squared, 4. And why am I pulling up this ratio? Because area is 2 dimensions. So I have unknown area, cm squared, to 20 cm squared, equals this ratio, because it's 2 dimensions, 9, which is our 2-dimensional ratio, to 4, 2-dimensional ratio, cross multiply. You have 4x equals 9 times 20. Get your hands off those calculators, friends, or hopefully you didn't use one. And x, 4 goes in there 5 times. The area is 45 centimeters squared. When you change dimensions, you change ratios. Last thing we're going to talk about is what happens when you have parallel lines and they create similar triangles and proportional segments. Got to get an L there. I'm going to take a triangle and slice it by a parallel line. And you're going to end up, if we do that, with triangles which are similar. Let me show you what I mean. So we're going to shrink this out a little bit. So it doesn't matter. You don't have to go through the mid-segment. Just I'd like you to trace PR and now slice with the parallel line to PR. So we got 2 parallel lines. You need to see this. Let's get some points here. We'll just call that, I don't know, HJ. The resulting 2 triangles, HQJ, and the larger triangle overlapping, PQR, are similar. Same shape, different size. You could also look at the same image exactly differently and say these segments here that I'm tracing are proportional. Why is this important? Because once things are similar or proportional, you can solve everything using proportions. So we're going to do, the name of the game here is you just need to match the sides up and mirror the direction. Match and mirror. Do that with me. Match the sides, mirror the direction. We're going to do a couple examples together. So here we have triangles sliced by a parallel line. The first thing I'm going to do is I'm going to pull them apart so you can see the 2 separate triangles. So I have a smaller triangle and I have a larger triangle. Now we're going to pull the information over. In this small triangle, this is 4. This side is going to be 6. Take away 4s, that's going to be 2. This whole side is x plus 5. This whole side is 6. Now what's true is because of the parallel lines, these triangles are similar, which means we can find a scale factor. So we take these 2 sides and we're going to reduce and find our scale factor. Cross this out, cross this out. This is a 1-to-3 ratio. So if we were to solve for x here, match, mirror the direction. 1-to-3, match, mirror the direction. 4 over x plus 5. Cross multiply. What's really nice is you can test these. 7 plus 5 is 12. Now let's check. 2 to 6 is a 1-to-3 ratio. 4 to 12 is a 1-to-3 ratio. And kudos, you got that right. Match and mirror. Match and mirror. Ready? Let's do another one. We have overlapping. Notice, just again, we have parallel lines. None of this works unless you have parallel lines. So we have one triangle. Try to draw this a little bit more to scale. Larger triangle. Let's pull over our information. This little guy is 10, and this whole guy is 18. Now that they are similar, you can make a proportion. So you want to find your scale factor first. I'm going to work right to left, and 2 goes in there 9 times, 2 goes in there 5 times, so I reduce 9 to 5. And now I'm going to mirror the direction. I'm going to go left to right. 9 over 5, 4x plus 13 over 25. Cross multiply. I'm going to bring the work down here. It's 9 times 25 equals 5 parentheses 4x plus 13. Let me get real close. Could you distribute and multiply the left and distribute? Absolutely, but I'm going to divide out the 5 to make it more simplistic. That's going to be 45 on the left, 4x plus 13 on the right. X equals 8. Match and mirror, match and mirror. Then we have proportional segments just with parallel lines. Transversals on parallel lines cut off proportional parts. Remember, it's all about matching and mirroring. Matching and mirroring. So here we have a set of parallel lines. Just get in the habit of always just tracing parallel lines. That just establishes in your brain your landmarks. And all you have to do is match the proportional parts. That's very, very important. So color code or squiggle. So this 20 is going to match with the unknown on the other side. This 36 matches with this. Wait a minute. That's not there. So look what you have to do. That's 36. Trace the 36. Trace the 20. And it's going to be 16. So match and mirror. I'm going to go left to right. 20 to unknown equals 16 over 36. Cross multiply. 16x, 20 and 36. We're going to divide by 16. 16. Now this takes a couple steps to do this. Watch carefully. 8 doesn't go into 36 or 20, so I'm going to start with 2. So 2 goes in here 8 times, and 2 goes in here 10 times. I'm going to just keep hacking away. 2 goes in here 4 times, and 2 goes in there 16, 8 times. 18. 2 goes into 36 18 times. 2 goes into 4 twice. 2 goes into 10 5. And you have one more 2 goes in here, 9. So you end up with x equals 45. Match and mirror. I'll do these two with you. So we know the 9 matches with this unknown. And then this squiggle matches with the 20. So we have to find the squiggle. The whole thing's 21. That's 9. 9 from 21 is 12. Now we cross multiply. 9 times 20, 12 times x. All right, 3 goes in there 3 times, 3 goes in there 4 times, 4 goes into 20 5 times, so x is 15. This one, wait a minute, they look like triangles. No, they aren't. They're undercover parallel lines, which means this 9 matches with the 15 going this way, and this 15 matches with 3x minus 2. I'm going to reduce on the left before I cross multiply. 3 goes in there 3 times, 3 goes in there 5. Now I'm going to cross multiply. 3x minus 2, 15 times 5. We divide out the 3. 3x minus 2, the 3 goes into the 15 5 times. So we have 5 times 5. Bring it over here. Good job. All right, friends, this page you're going to do completely on your own. I am not going to give you the corrections. I'm going to correct it in class, completely on your own. Please box your answers. Remember to do a summary of what you learned in today's lesson.